In today's lesson, we're going to discuss the real numbers. And specifically, we want to be able to identify the various kinds of real numbers that we're going to be dealing with. We want to learn how to use interval notation so that we can write solutions to inequalities and other types of questions. We want to be able to graph those things properly on a number line. We need to know some of the properties of real numbers, and we need to be able to find the absolute value of a real number and the distance between two numbers on a number line. All right, the first type of real number that we're concerned with are called rational numbers, and rational numbers are basically just your numbers that are represented by a fraction, right? Any number you can represent as a fraction is considered a rational number. So 0.5, even though it's a decimal, is still a rational number because 0.5 really is the same thing as 1/2. Okay? Irrational numbers are numbers that cannot be represented by fractions. So the two kind of categories are you're looking for a decimal expansion of the number that goes on and on forever, and it doesn't repeat, it doesn't have any type of pattern. Or it's one of those kind of well-known numbers like pi, which is like this, right? So you can think of it as two separate things, but it really is the same thing. Pi is really that number, 3.14, I think it's 159, et cetera, et cetera, et cetera. And there's no pattern. It never repeats. And then square root of 5, you can see there's no pattern. It doesn't repeat. You might be asking, okay, well, what about something like 0.3 repeating? Is that irrational? No, because that repeats, and that equals 1/3. So if the decimal can go on forever, but if it repeats, it ends up becoming a rational number. Interval notation. It's really good to know what these things mean. It's just quick, easy shorthand. This vertical bar always means such that. Sometimes it's written ST for such that, but the vertical bar is quicker and easier. So this is the set of all x's such that a is less than x is less than b, and then there is the graph. You'll notice the difference between these two graphs is round brackets versus square brackets, and the difference here is strictly greater than, strictly less than, and less than or equal. So square brackets is when you have less than or equal to or greater than or equal to, right? And round brackets are strictly less than or strictly greater than, etc., etc. So that's a good thing to remember. Round brackets are less than or greater. Square brackets are the less than or equal or greater than or equal. Some examples, simple examples, right? X is in between -4 and 5, and they're both, right, strictly less than, strictly greater than. So you can see those are round, kind of hard to tell. Here we have x is greater than or equal to 1.7, so that's where you get your square bracket. We should also point out how to write these things in interval notation with just these types of things. You'll notice that these symbols, right, this round bracket and this round bracket, correspond to these round brackets. So this one here has a square bracket here, but a round bracket up there, because we always have round brackets for infinity, because you can never equal infinity because infinity goes on forever. The same would be true if we had the set of all x's such that x was less than 2. We would have the number line here with 2, and if we made it a less than or equal to, we'd put a square bracket in here, and then we would have everything to the left of it, right? And then if we wrote that in interval notation, we would have negative infinity, comma, 2 with a square bracket. Some more examples. Here's a similar one to the example I just did, only now it ends at -5 instead of negative infinity. All right. And then here's an example with negative infinity and something that is strictly less than. Properties of the real numbers. We have the commutative property of addition. We know that anytime we add two things, we can add in either order and it's the same, and the same goes for multiplication. Oftentimes, by the way, whenever you have a rule for addition, multiplication tends to have the same rule. And then a lot of times subtraction and division don't work, right? So they kind of go together both as not working. 3 times 2 is 6, 2 times 3 is 6, right? 3 plus 2 is 5, 2 plus 3 is also 5. The associative property of addition and multiplication just means we can do this same stuff but with more than two of them. So a plus b plus c is the same thing as a plus b plus c, and you go, well, no, duh. But the difference is these brackets, right? These brackets tell us first we add b and c, then we come back and add a, whereas this tells us we add a and b first, then add c. But since we have this commutative property, this stuff kind of comes along for the ride. Same thing here. This says multiply b and c first, then multiply a. This says multiply a and b first, then multiply c. It's kind of related to your commutative property. It's slightly different, but it's all in the same kind of. Here's your additive identity. Anytime you add 0 to something, it doesn't change it. And then your additive inverses, right? Anytime you add the opposite number to itself, you always get 0. Your multiplicative identity is 1, and the multiplicative inverse is 1 over the number. And then the last property that we have is the distributive property. And it's kind of like foiling, but only with one thing, right? So a times b plus a times c. So you kind of have this two-piece thing. And that's the distributive property. Here are some examples, right? Commutative property. Here's the distributive property kind of in reverse, which is more of what we need to be able to do in algebra, is take this and factor out the 3. So when we're factoring out the 3, we're really doing the distributive property in reverse. And then here all we're doing is using the associative property to put the letters together and then leave the number out by itself. Okay, absolute value. I know a lot of you kind of learned absolute value as just being the positive of something, but the true definition of absolute value is its distance from 0. So that's why the absolute value of -6 is 6, because -6 is a distance of 6 units from 0. So either way you want to think about it, you're going to get the same answer, right? It always gives you a positive answer because distance is always positive. You know, you can't be -5 feet from something, at least not in math. You can in physics, but that's a discussion for another day. So once you understand that absolute value is a distance, then memorizing this whole thing really isn't necessary, because you just know that whatever number is in here, you get the positive version on the outside. And that's what all this gobbledygook is saying, is that if a was a negative number, right? So a was less than 0, so the a that was sitting here was a negative number, then the answer is the opposite of it, right? So it's very confusing the way this is written. You guys know what absolute value is. It's just you always take the positive amount. The distance between 2 points on the number line is very simply just the absolute value of a minus b. And that's why if you think about it as distance, this helps a little bit. So to find the distance between -2 and 3, you simply just take the difference between those two numbers and get the absolute value. And you'll see that it doesn't matter in either direction, right? If you do 3 minus a minus 2, it becomes 3 plus 2, which is 5, and you get the absolute value of 5. So absolute value is really a distance on the number line. It's the distance from 0, and to find the distance between 2 points, you're just taking the difference between those two numbers and then taking the absolute value of it. So just pick it either direction, doesn't matter, a minus b, b minus a, either way, and then take the positive. That's it.